Hey everyone, so today we're going to tackle this buffer problem, and I'll start by reading it out. A student made a mistake while preparing an acetic acid acetate buffer. They intended to prepare 100 milliliters of pH 4.85 buffer, but combined 15 ml of 0.1 molar acetic acid with 85 milliliters of 0.1 acetate by mistake, resulting in a pH of 5.5. They used a 3 molar HCl solution to correct the buffer's pH. What volume, and they're asking, what volume of 3 molar HCl solution must be added to correct the buffer pH to 4.85? And what they've given us is the Ka of acetic acid, and these are our four options. So we need to figure out a way to pretty much get rid of some of the acetate using HCl so that the pH goes down and we make more acetic acid. And so actually, let me write out the full equation of what's happening here. We have CH3COOH, and then we have some CH3COO minus, or Na actually, and then plus water, and then we get on this side we get some of this dissociating, so we get some hydronium ions, and then we also get CH3COO minus, which is the conjugate base of our acetic acid or acetate. And this is pretty much our buffer solution. And what we want to do is we have too much of this. So we want to add some HCl because HCl is a strong acid, and like all strong acids, they dissociate completely. And in doing so, we get to tack on a hydrogen ion. And this CH3COOH can turn back into acetic acid, thus lowering the pH. So what we can use to figure this out is, actually, let's write out what's given to us. So what's given? Change the color to make it a little bit clearer to see. So we have a pH. Well, our intended pH is 4.85. Our actual pH is 5.5. We have 15 milliliters of 0.1 molar acetic acid. We have 85 milliliters of 0.1 molar acetate, or CH3CONA. And this can kind of be like any metal. And we have 3 molar HCl to correct our mistake. So what we can use in this situation is the Henderson-Hasselbalch equation. And it's really good for buffers. And usually you can figure out a way to use it in that situation because it combines pH with pKa. In this case, we got the Ka. So there's a hint right there that we probably need to use this. So we have the pKa plus the log of the ratio of conjugate base over conjugate acid. So we have this over this, and I should say concentration of conjugate base over the concentration of the conjugate acid. So in this situation, this equation works both as if you use the concentration or if you use the moles of the conjugate base and conjugate acid. In this case, the molar concentrations are the same, and so this would just be 1, and the log of 1 is just 0, and so we just get the pH is equal to pKa, but we don't really want that. We want to figure out exactly how much HCl or how much acetate we want to turn back into acetic acid. So we can figure out, let's figure out the moles of each of these in our solution first. So we have 15 milliliters, and we have 0.1 molar. So what we can do is we can divide this by 1,000 milliliters, and this will give us liters times 0.1 molar, which is the same thing as moles per liters. And so those liters will cancel out, and we'll just get our moles at the end. So what we can do here, let me grab a calculator. So what we have here is 1.5 times 10 to the minus 3 moles. And that's of our acetic acid. Now we can do the same thing to figure out the moles of acetate in our solution. So we have 85,000 milliliters. That's just times 1 liter. Should have had times 1 liter over here too. Times, again, 0.1 moles per liter. And in this case, we get 85 divided by 1,000. It's just going to be 8.5 times 10 to the minus 3 times 0.1. So we have 8.5 times 10 to the minus 3 moles. Okay. Now that we've found the moles of this, we can put this whole equation in terms of moles, which will make it much easier to find out exactly how much HCl we need. And as I said before, we're trying to get rid of some of the acetate and turn it back into acetic acid so we can lower the pH while still maintaining the buffer. So what we can do here is we can have our pH is equal to our pKa plus the log. And now what we're doing is we're not dealing with concentrations, we're dealing with moles. And so what we can do is we have our conjugate base over here, which is 8.5 times 10 to the minus 3 moles. And so for our conjugate base, we're lowering it. So we have minus x. And this will be a placeholder, or will represent the amount of HCl we want to put in. And then we divide that by 1.5 times 10 to the minus 3 moles. And then we're adding HCl, which will dissociate completely and donate the hydrogen to our acetate, which will increase the moles and the concentration of our acetic acid, which will lower the pH to what we want. So this will be adding some amount of moles of hydrogen, in this case HCl. So now we can fill in the rest of the stuff that we need. So our intended pH is 4.85. Our pKa is anytime you see a P in front of something, it's in chemistry it means the minus log of whatever it is. So in the case of pH, we have the minus log of our H, of our hydrogen concentration. And in the case over here, we have the minus log of our Ka value. So we have the minus log of 1.8 times 10 to the minus 3, to the minus 5, my bad. To the minus 5, and then that's plus the log of 8.5 times 10 to the minus 3 moles minus x over 1.5 times 10 to the minus 3 moles plus x. And so what we get is, here, let me make some room. Still getting used to this program. So just keep this over here. And then we have some room. So what we get is 4.85 is equal to, I think the minus log of this is 4.74. And then we have plus this. So plus the log of 8.5 times 10 to the minus 3 moles minus x, and then over 1.5. Actually, so this should be the log of all this. So 8.5 moles minus x over 1.5 times 10 to the minus 3 moles plus x. And what we get at the end is we get x is equal to 2.87 times 10 to the minus 3 moles. And this is how much HCl we need to add. So now we can turn this, given the concentration, given that we have 3 molar HCl, we can try to figure out exactly how many milliliters or what volume will give us these many moles in this solution. And so how we can do that is, we know 3 moles is the same thing as 3 moles per liter. And that's how much HCl we have. And we have the moles. So what we can do is we can have 3 moles over liters times some x value, or let's call it y, because we already used x before, times y is equal to 2.87 times 10 to the minus 3 moles. Actually, let's not call this y. Let's call it v for volume. So how I set this up is I'm trying to find the v value that in liters that'll cancel out with this liters that'll give us this value of moles, and that'll tell me the volume of HCl that we need. So v is equal to 2.87 times 10 to the minus 3 divided by 3 moles per liter, and this is moles over here. So those moles cancel out, and this 1 over liters comes up, and so we'll get exactly the amount of volume that we need in liters. So 2.87 times 10 to the minus 3 divided by 3, and so we get 9.56 times 10 to the minus 4 liters. So now we can convert this into milliliters, multiplying it by 1,000, and we get 0.956 milliliters. And so that is the volume of HCl we need to correct this buffer and lower its pH to what the desired 4.8 pH. And that's option D.